Hello. Today we're going to talk about Chapter 23, Comparing Means. What I mean by that is this example. So, let's say you wanted to see if there's a difference between the batteries of brand name versus a generic type. Okay, so you tested out a whole bunch of batteries, you recorded how long they lasted, and now you want to compare the means. Okay, so think about this. You wouldn't necessarily know anything about the population. Okay, that's an example of what we're going to be talking about today. And this purple box is literally just a footnote from the textbook, which is just another reason why I like this textbook. But again, it might be outdated. I don't even know if some of you guys know what an iPod is. It's basically an iPhone that only plays music. I know, that sounds so silly, but it used to be a time where your phone couldn't play your music. Yes, and then CDs are like DVDs, but oh gosh, those are probably outdated too. Ask me in class. Be happy to show you an old version. I still have CD-ROMs. Yeah, oh gosh. We'll talk. All right, so to compare two means, the best way is to visualize it. And the best visualization usually is a box plot. So see, comparing the two side by side really is helpful. So once you have them side by side, you can create that comparison, which isn't really different from comparing two proportions. All right. However, this time, the parameter of interest, we want the difference between the two means. Okay, so you take one mean minus the other mean. All right, so we remember that independent random quantities, variances add. So the standard deviation would be this. We still don't know the true standard deviations of the two groups, so we need to estimate and use the standard error. Okay, so we're using the standard error because we don't know the true proportions. The true mean, sorry. True standard deviations. I knew what I was saying in my head. It just wasn't coming out. All right. Because we are working with means and estimating the standard error of the difference using the data, we shouldn't be surprised that the sampling model is a student's t. Okay, so the confidence interval we build is a 2-sample t-interval, and the hypothesis would be a 2-sample t-test. So that's what we're doing in this chapter. Now, when the conditions are met, the standardized sample difference between the means of two groups is this formula and can be modeled by a student's t-model with a number of degrees of freedom. All right, but here it's a special formula. We'll get to that. And then the standard error would be this formula. Of course, we can't use any of that unless our assumptions and conditions hold true. So make sure you do your assumptions. We have our independence assumption. So we check the randomization and 10% condition, right? We know what these are. And we only check the 10% if we have a very small population or an extremely large sample, like the extremes. All right, the normal population assumption, so the nearly normal, must be checked for both groups. Okay, so again, you're comparing means, so you're comparing two groups here. And the independent groups assumption. The two groups we are comparing must be independent of each other, which makes sense. If they're not independent, we'll get to that in Chapter 25 after this. Now, when the conditions are met, we're ready to find the confidence interval for the difference between the two means. So here is our confidence interval, and here is our standard error. The critical value, so the t star, depends on the particular confidence level that you specify and the number of degrees of freedom, okay, which we get from the sample sizes and a special formula. This special formula is this one. Pretty gross, right? You could plug it in and work it out, all right? Or we could just use technology, right? Technology can tell us what the degrees of freedom is. Now, for testing the difference between the two means, we have our hypothesis test. Again, your null hypothesis is you're subtracting them, And usually, it's almost always, it's going to equal 0. Okay, you want that difference to be 0. Okay, let's see. Here we have our standard error. All right, so all of this kind of follows a similar, familiar pattern, right? When the conditions are met and the null hypothesis is true, this statistic can be closely modeled by a student's t-model, number of degrees of freedom, and we use that model to obtain a p-value. So we're creating a model and then finding our p-value. All right, back when we had proportions, we know it's standard deviation. So when testing the null hypothesis that two proportions were equal, we could assume their variances were equal as well. So we pooled our data. But for means, there's also a pool t-test that it assumes the variances in the two groups are equal, but we have to remember there's no link between a mean and its standard deviation. So if we're willing to assume that those variances of two means are equal, we can pool the data from two groups to estimate the common variance and make the degrees of freedom formula much simpler. Okay. We are still estimating the pooled standard deviation from the data, so we use student's t-model, and the test is called a pooled t-test for the difference between the means. So if you want to assume that the variance of the two means are equal, you put them together to get the variance. Now, the conditions for the pool t-test and the confidence interval are the same as for our earlier two-sample t procedures. Okay. For the hypothesis test, our test statistic is this, which has degree of freedoms this now. Okay, which kind of makes sense. You're adding both of them, and now you're subtracting 2 because there's 2 of them. And our confidence interval is this. So, when should you use pool t methods rather than two-sample t methods? Okay, never. Well, hardly ever. The advantages of pooling are small, and you are allowed to pool only rarely when the equal variance assumption is met. So, don't. Okay? That doesn't happen. Okay? It's never wrong not to pool, but it's one of those things that it's very, very rarely can you. Like, is it usable info? Think of it like that. All right, some of you might ask, why not test the assumption that the variances are equal? Well, there's a hypothesis test that would do this, but it's very sensitive to failures of the assumptions and works poorly for small sample sizes, which is what we usually have. Okay? Just a situation we might care about, right? So the test does not work when we really need it to. Okay, so that's not helpful. All right, is there ever a time when assuming it makes sense? Well, yes. In a randomized comparative experiment, we start by assigning our experimental units to treatments at random. Each treatment group therefore begins with the same population variance. They should be the same, and then we're testing the difference. Okay, in this case, assuming the variance are equal is still an assumption, and there are conditions that need to be checked, but at least it's a plausible assumption. So that's when it would make sense to assume that the variances are the same. Okay, so let's do some examples. So here's the first one. We're going to do the heartbeats of smokers. Why don't you take a minute, pause it, read it, and then I'll go over it. Okay, so you start with your hypothesis. So we have the difference is 0, smokers and non-smokers. You may want to label that. S means smokers and S means non-smokers. Let's see, you have your assumptions, random samples, each group is less than 10%, and we are told the data appear normal. Okay, so we proceed with the two-sample t-test. So here you would describe everything, the number in your participants, the mean and the standard deviation of both, and let's see, our degrees of freedom would be 26 plus 32 minus 2. That's where we got that here. So here we go to our calculator and we can go to statistics, test, two-sample t-test. We just type in everything, our mean, standard deviation, number of participants. That's my smokers. The second one is my non-smokers. All right, it doesn't equal for the hypothesis. I didn't do pooled, and I calculate. All right, so notice here, it looks like I wrote the wrong p-value, right? However, look at the end of it. It says that E -4. A lot of people miss that. You know what that is by now. That means you got to move that decimal when it's negative to the left. So we get 0.001, 1, 2, whatever. Okay. Let's see. What if you had decided to pool your data? Well, this was it not pooled, and this was it pooled. Okay, so you can see the p-value isn't much of a difference. Okay, you'd have to think about when you would want to pull something. Okay, whether or not you, if you think it's necessary. Okay, here, let me label these. Okay, so let's do our next example. So here we have saturated fat in pizza. All right, so you want to write this stuff down. Maybe go ahead and put that in your list. All right, so pause it, take a second. Okay, so here we're going to have our hypothesis right here. Then we're going to have our conditions. Make sure you label them. Again, remember box plots or probability plots can help you, not box plots, histograms. Histograms or normal probability plots can help tell you if they assume they appear normal. Then you have your conditions are met, so we're going to use the t-distribution, the two-sample t-test. So then we have our mechanics for that two-sample t-test. You list all your information, the degrees of freedom, and then here we have all of our info. Okay. Okay, so you're probably wondering how I got the degrees of freedom. Well, I put it into my calculator. I started by putting all these numbers into each list. Brand D was in list 1, brand PJ was in list 2. Then I did stat test, two-sample t-test, went down here, and I calculated it. Notice there, they did the degrees of freedom for me, so I didn't have to plug it into that crazy formula. Okay, so use that, that's helpful. All right, so then after that, we make our conclusion based on our p-value. Well, that's really small. That's lower than most alpha levels. So we have sufficient evidence that the average saturated fat content of brand D is not equal to PJ. So there's a difference between the two. Now let's construct a 95% confidence interval. All right, so take a second, see if you can figure it out, and then I'll go through it. Okay, so this is how you can do it by hand. If you wanted to do it with your calculator, since we already have the data in there, you go to statistic, test, where is it? Two-sample t-interval, and then list 1, list 2, confidence interval, bam. Spits it out for you. Okay, so we got the same numbers. All right, now notice if you do that, make sure you list everything about your two-sample t-interval, all the important stuff. Okay, you could even just label the formula. Okay, they give you everything you need. Okay, so what can go wrong? You want to watch out for your paired data. So the independent groups assumption deserves special attention. Make sure that the groups are not paired because that's something totally different in chapter 25. Okay, look at the plots, check for outliers and non-normal distributions by making and examining the box plots or the normal probability distributions. All right, and this is everything you should have learned in this chapter. So hopefully this one wasn't too bad. I think this is probably one of the shortest videos I've made for you guys. If it doesn't make sense, please let me know. Be happy to talk it over with you.